Hi, I'm Chris Martinez, and for my modeling and automate class, we were asked to model a suspension system for an automotive vehicle. For applying intelligent suspensions to improve passenger comfort and vehicle stability, we require the understanding of dynamic behavior of passive, active, and semi-active suspensions in terms of vertical vehicle dynamics. But first, what are suspension systems? Suspension systems are highly important in cars due to all the functions they have while the automobile is moving. The main functions can be highlighted as maintaining the wheels in the constant friction with the contact surface and ensure the driver's safety, reducing the impact effects on the car cabin caused by the irregularities on the road, support the weight of the vehicle, and stabilize the movement of wheels, making it easier and safer to keep the vehicle in the required direction. For the commercial solutions, there are three types. In order to anticipate potential road defects, active suspensions regulate the vertical movement of the wheels and make use of numerous processors and sensors. The sensors continuously track how the anti-lock brake system, vehicle frame, and suspension are moving. For the properties of the parts, springs, and dampers in the passive suspension system are fixed according to the design objectives and the intended use. The suspension designer chooses these qualities. A passive suspension has the ability to store energy via a spring and to dissipate it via a damper. Semi-active suspensions is a type of automotive suspension system that controls the damping force of the shock absorber in response to input from the continually varying road surfaces. It is intended to approximately implement the active suspension with a damping force adjustable shock absorber. Semi-active suspensions may be implemented by skyhook control. There can be different equations for mathematically modeling the suspension systems. Each equation represents different correlations for this sample study. The equations obtained have the purpose of modeling the relation between the sprung mass and its vertical displacement. For this activity, we focus mainly on the quarter of a car passive suspension. We chose this diagram and we chose its main variables and what we're going to call it. For M1, we have sprung mass, unsprung mass, stiffness coefficient of suspension, vertical stiffness of coefficient of tire, damping coefficient of suspension, damping coefficient of tire, among others. And using the second law of Newton for each of the masses and the third law for their interaction, we can get this equation, which shows us the relation. And by doing this, now we perform a Laplace transform in order to find the transfer function. So taking those equations, we do this so we can establish the transfer functions for the displacement, which are these two equations left. And use these previous equations for give the transfer function, we can also obtain the state space representation, which also have some variables, which we name x, y, u, a, b, c, and d. And well, these basically are putting all the equations together. We are applying the state space correlation by doing establishing some matrices of the system, and therefore we are left with this equation of the state space correlation and how is this going to work. For the quarter of a car semi-active suspension, we are shown this diagram, which we also have to put some variables, some names. We have to establish what are going to be those variables in order to us to improve and to put an equation. And again, using the principles from Newton's law, the motion equations can be obtained as okay, we can be obtained as these also two equations, and we can show the relation about it, and then we do the Laplace transform in order to apply both equations to find the transfer function. Well, after applying these all equations, we do the Laplace to obtain the transfer function, and once we have the transfer function, we can use these first equations in order to find our the line of correlation between those variables. And for our last quarter of a car, we have the active suspension, which we use this diagram. And in order to model a quarter car of a car active suspension, we establish this variable shown also, um, and therefore we apply also these variables into, put it into an also an equation and differential equations. And once we have all the differential equations, we apply the second law of Newton for each of the masses and the third law for the interaction, and we are left with this. And now with this equation, we do the Laplace transform to find the transfer function and establish transfer functions for the displacement. And well, use the previous equations, we are left with these two. And well, what are the explanations of these obtained simulations? By applying MATLAB and Simulink for the quarter of a car for a passive suspension, we are left with this simulation, which we can see over here. And we can see how is this going to behave in order that the suspension is going to isolate in a manner that's going to be from a hard suspension, and it's going to be lower even here. And for the other simulations, well, this type of suspensions, no matter the input force, we always use the same damping coefficient in terms of user experience. The bigger the input force, the more the shaking of the car will be. And for the quarter of a car semi-active suspensions, we also made a simulation. And this type of suspension based on the input force will always vary on damping coefficient. In terms of the user experience, the bigger the input force, the more the bigger of damping coefficient will be. But this will remain constant of decrease rapidly depending on the control system. And for the last one, here are the last simulations for the quarter of a car active suspension, which we can see how it behaves in a different manner of the previous two. In this type of suspension, given the input force, it will generate a response force in order to decrease the energy absorbed by the chassis of the car. In terms of user experience, of course, exerted by the road will be damped by a force generated by the suspension in order to give the user the smoothest ride possible. So the active suspensions will give us the best experience. So the parameters and the code used for these simulations, we basically use the M1 of 250, M2 320, K1 80,000, K2 500,000, B1 350, and B2 5,020. And well, this is part of the code used in MATLAB. Here we show you how we apply the previous parameters. And well, this is part of the MATLAB code, which is for each one of the suspension systems. The first one is the passive, the second the semi-active, the third one, the best one, the active suspension. So basically, in conclusion, the active suspension system give us the best experience and give us the smoothest ride ever. So, well, thank you, and thank you for your time. Yes,